In this video, we're going to be looking at circuits that have multiple EMFs or multiple voltage sources in them. In some ways, you've already actually seen this and been doing this without realizing it, but only for a very specific case. This is going to give us a chance to expand how we use the loop and junction rules and Ohm's law to look at circuits with multiple batteries primarily is what we think of. So if there's multiple EMFs in series, you already kind of know what to do with this, right? If you imagine a 20 volt battery cell here connected to a 20 ohm resistor, that would give you 1 amp of current. But what if you had two 20 volt battery cells connected in series? Notice it's long, short, long, short. So this is basically like putting two batteries one after another, which is something we've already done. We usually connect them directly together as a battery pack. Here there's a little space between them, but the principle is the same. As you were to do, if you do the loop rule and you go around this, you go plus 20 volts, plus another 20 volts, minus 40 volts across the 20 ohm resistor, giving us 2 amps of current. And then we can go a little bit further and say, well, what if we flipped one of those batteries around? Well, we'd go plus 20 volts if we're going clockwise around the loop, then minus 20 volts because we're going from high to low potential, from positive to negative. And so the net effect of those two 20 volt battery cells pointed against each other is that there would be 0 voltage and therefore 0 current. Now, practically speaking, doing that with two batteries, they're trying to push charge in opposite directions, can cause them to wear out and heat up faster. So we don't usually do this in practical terms, but that is what would happen. What about in parallel? Well, in parallel, you can use batteries that are not the same voltage, but when you do that, you actually get current flowing the wrong way through the battery. This is done, if you were to color code it, right, you would have red across the top and blue across the bottom. So there would be 20 volts across each branch, across the two batteries, and 20 volts across the resistor. And so we would have 1 amp of current. What this does is it doesn't change how much voltage the bulb or the resistor has, but what it does is it provides two different sources of current. So each of those batteries doesn't have to provide as much. So if you've ever put multiple batteries inside of a device, sometimes you put them in so they sort of, if you imagine positive one way, negative the other way, that's usually because they're in series, looped together to increase the voltage. But if you've ever put batteries in where they're designed to be pointing the same direction, that's probably because the 1.5 volts or thereabouts of a battery is sufficient voltage, but you want additional current so that it can, last longer. Practically speaking, we often do this in something like a big battery pack, whether it be like a power tool with a battery pack, or even on a larger scale like an electric car. Those battery packs usually take cells and have some of them in series to increase the voltage, but then also many of those in parallel to provide a lot of current at once, which is what you need to accelerate, a multi-ton death machine to highway speeds. So what do we do with circuits if they're even more complicated than that? What if instead of just having all the batteries next to each other, we've got a battery and a resistor and a battery and a resistor on two different branches? How do we find the current and voltage here? We can't really color code this circuit because where would the red be? Where would the blue be? What happens as you go across these resistors? And so we want to find the current and voltage values for each thing. So we need to come up with a slightly different technique. And the main technique we have to do is to apply the loop and junction rules, but with slightly more, care. And we can't really use the equivalent resistance here because they don't just combine back to one thing connected to one battery. So here's what we do. We start and we redefine a loop as any complete path around a circuit, right? When we started, we sort of said, well, let's start and end at the battery. But now that we have two batteries, that's not really viable. So we could draw any loop we wanted to. And so I would say there's plenty of loops here. There's 3 different distinct loops. There's one that starts at the 100 volt battery, goes through the R1, R3, and back. That's sort of outside loop. There's a loop that goes from the 100 volt battery to R1 to R2 to the 20 volt battery and back, kind of going the wrong way across that 20 volt battery. And then there's the one that starts at the 20 volt battery and goes to R2 and R3 and back. So we have those 3 different branches, which means there could be we also have 3 different branches, which means we could have 3 different currents, right? One running through R1, through R2, and R3. Each of those resistors are on a different branch. So what we're going to do is we're going to write 3 different independent simultaneous equations using our loop and junction rules, hopefully hitting every variable in multiple places so that we can combine them together and solve a system of equations. So here's how it looks. We're starting by picking our best guess at the direction of the currents. So I am going to guess, just looking at those batteries, that current comes out of the 100 volt going up and around. So that's I1. Current from the second battery goes up as well, the way it would normally flow out of a battery. And then at that junction at the top, those 2 currents come together and I3 goes out through the resistor. This may or may not be correct. If we guessed wrong, we picked the opposite direction of what's actually happening, the value for I that we get out of our result will end up being negative, and we can go back and fix our diagram. So the most important thing with this technique is that you stick with your guess until all of your calculations are done. You don't want to change it up in the middle, otherwise that will confuse things. So I'm going to start with the junction rule because there's really only one equation from that, right? I1 plus I2 equals I3. Whether I pick the top or bottom junction, I get the same thing, right? At the bottom, it would be I3 in and I1 and I2 out. So we would get that same thing. And those two, don't really give us new information. So it's up to you which way you want to think about it. So we need to pick one of them as an independent equation. I'm going to pick with I1 plus I2 equals I3. And then we can move on to the loop rule. We're not going to worry about units here because that just is complex when we're writing it out. And you'll see what I mean, right? So the big outside loop, we've got 100 minus 2 ohms times whatever current I1 is, right? That's using the loop rule and Ohm's law simultaneously. Notice it's negative because as we go in the direction of current across a resistor, we expect to drop voltage. And then we do the same thing over R3, 20 ohms times I3. Again, negative because we expect a voltage drop coming back to 0. We'll do the right-hand loop, which is the 20-volt battery, minus 2 I2 minus 20 I3 equals 0 as well. There's actually a third one we can do. And this one, you got to watch out for the signs because if I do the left-hand loop, I do plus 100 because I'm going the direction across the battery that I would expect, gain, minus 2 I1. And then now watch out because I'm going the wrong way across resistor 2. I'm going against what I think is the current. So I have to call that plus a voltage gain going that way around the loop of 2I2. And then notice I'm going the wrong way across a battery from high to low. So that becomes a negative 20. The first 2 are definitely the easier ones to draw, but there are cases where you need one that has these negative signs where things flip. So continuing with that, right? The rules are if you go from the negative to positive terminal, as we usually do, that's a positive voltage from a battery. If you go from the positive to the negative terminal, that's a negative voltage from the battery. But with resistors, if you go with the current, that's a negative voltage change. It's a drop because that's normally what resistors do. And if you go against the current, you get a positive voltage change or a gain, right? So those are the rules when we're going around a loop for batteries and resistors. You may need to come back to this as you start doing practice problems, but that's kind of what's happening there. All right. We've got our various loop rule equations here. There's really only 2 of them that are completely independent, right? Left and right are the same together as the big equation, right? Which hopefully you can see that. So we're just not going to use the left equation because the left was the more complicated one. So now we have 3 simultaneous equations. Current 1 plus current 2 equals current 3 from the junction rule and 2 from our loop rule. And now it's just a matter of doing algebra and solving simple systems of equations. There's algebraic methods, right, where I'm going to solve and substitute in for that I1. I get that equation. I have that other one. I can add them together. We end up with this with only one variable, and we get I3 is about 2.86 amps. Once I do that, I can go ahead and substitute that back in, solve that equation for I1, then go back and solve that for I2. And notice I have a negative sign, which means I picked one of my directions of current flow incorrectly. So what that means is that current 2 is actually going down against the battery, which hopefully makes a little bit of sense, right? This 100-volt battery is pushing much harder, if we want to use that analogy, than the 20-volt battery. So current I2 actually flows downwards. Now that we have all of that, we can go back and use Ohm's law and get the voltages because we have current for each of these. We can plug all those in. We can double check with the loop rule that if you go around 100 volts minus 43 volts, minus for the 57 volts gets you back to 0, and so on. There's another method you could use, and that is to use a matrix method. Now, I'm not going to go into detail on this, but if you have these equations, if you set them up into a form where you've got variable 1, variable 2, variable 3 equals number, I1 plus I2 minus I3 equals 0. You've got 2I1 plus 0I2 plus 20I3 equals 100. 0I1 plus 2I2 plus 20I3 equals 20. You can put them into an augmented matrix, right, where we just put the coefficients 1, 1, negative 1, 0, 2, 0, 20, 20, 100, 0, 2, 20, 20. And then you can do reduced row echelon form, and that'll give you a form that will tell you what the coefficients or what the values of I1, I2, and I3 are. And then once you've done that, you can go back as well. So that's just up to you if you want to use that method. And, it's not something we do all the time, so it may or may not be worth it to you. All right. So that's multi-EMF or multi-loop EMF circuits using the loop and junction.